So let's start 12.3, Introduction to Polynomials. And we have various objectives to accomplish today. And the first thing we're going to do is I'm going to talk about the meaning of the word term. So a term is a real number or the product of a real number and one or more. I'm going to put on or more in parentheses variables, each raised to a power of some positive whole number. So let's just look at a whole bunch of examples. 5 is a term. 7 times the variable x is a term. 11 times the variable x times y is a term. 1/2 times x squared is a term. Minus 3xz cubed. All of these are terms. So let's give you a little bit more vocabulary. 5 is just called, it's not a product of any variable, it's just called a constant, or sometimes a constant term. 7x is called a variable term. And 11 times xy is called a variable term. And so is 1/2 times 1/2 times x squared. That is also a variable term. And you guessed it, so is this last one. This is also a variable term. If you don't like the word variable, you can call this a term with an unknown term, or a term with an unknown. So if I want to be more specific, we could say 7x is a variable term in the variable x. 11xy is a variable term in the variables xy. 1/2 x squared is a variable term in the variable x. Minus 3xz cubed is a variable term in the variables x and z. When I want to be more specific, for the most part, we will be dealing with single variable terms and constants. So let's define a polynomial. Well, let me give you some examples before I go on of things which are not terms. Different color here. 7 divided by x is not a variable term. Why? Because using our rules of exponents, this is equal to 7 times x to the minus 1. And if we go up here and look in my definition, the variable power must be some positive whole number, and minus 1 is a whole number, but it's not positive. So keep that in mind. So our variables, if they have powers at all, then they have to be raised to a positive whole number. So now let's look at our next definition. This is a very important definition, and it's a really easy definition. And guess what? The definition is going to use the very concept I just reminded you of. So a polynomial, that's what we're defining, is the sum, or for that matter, or difference of variable terms. Now sometimes we want to be more specific, and we will talk about a polynomial in the variable, we include that to be plural, x, y, z, and the list is always finite. Now, these are really important in math, but for you all, pretty much we're going to be talking about a polynomial in the single variable x. Although we're going to be looking at some other types of polynomials that are in more than one variable, or a polynomial in a single variable that's different from x. So let's look at some examples of a polynomial in a single variable x. 3x plus 1. So it's a sum of terms. 3x is a variable term, 1 is a constant term. 4x squared minus 3x plus 2. That's also a polynomial. It's a polynomial in the single variable x, because there's only one variable in the sum of terms. Let's look at another example. Minus 3 plus x halves plus 4x to the fifth. This is also a polynomial. You might be bothered, it's a polynomial in the single variable x. You might be bothered about this term. But recall, x halves is just shorthand for 1/2 times x. And let's do another example. I'll give you an example of a polynomial in two variables. 4x squared y plus 3x plus 7y. Now notice, each term doesn't have to have both variables in it, but the sum of terms have more than one variable, and they are x and y. Indeed, just 3x plus 7y would be a polynomial in the variable x and y, just like this is. And 4t squared minus 3t plus 1/10, that's a polynomial in the variable t. So that right there, that's my version of t. So the variable, we will often name it, but many times for us, we're going to be just looking at polynomials in the single variable x, and that's it. But I do want you to be aware that there's other polynomials out there, in particular polynomials in the single variable y, or polynomials in the single variable z, or polynomials in the variables x and y, or for that matter, a polynomial in the variables x, y, z. And literally, one term is a polynomial. So If you want to add plus 0 to make it a sum of two terms, that's fine. So a single term is a polynomial. So the polynomial is a sum or difference of variable terms, or a single term. Of course, you can add 0 in there to make it a sum. So I'll just make that more explicit. So let's break some more things down. So let's look at a typical polynomial like you're going to be seeing in this class. 4x squared minus 3x plus 1. So that's a polynomial in the variable x. And it has three terms. First term, second term, third term. This is called the constant term. And these two here are the variable terms. So let's focus on the variable terms for just a second. So the variable terms for x squared are made up of two parts. They are made up of the variable and some multiple of that variable, which is called the coefficient of that term. So a lot of stuff I'm hitting you with, it's not really hard, but let's again look at this. So here's my polynomial. It's right here. 4x squared minus 3x plus 1. It's a sum of terms, so that makes it a polynomial or a single term. It has a constant term, which is 1, and two variable terms. And of the two variable terms, one of them has a coefficient of 4, and the other has a coefficient of minus 3. So we have almost extracted all of the information we can about this polynomial, except there's one glaring omission. And we're not saying anything about the fact that this term here, x is squared, this term here, x is not squared, but rather raised to the power of 1. So that introduces our final concept, and it has to do with degree of a polynomial term. So for right now, let's deal with polynomials in just one variable. Like you see here. This is our paradigm example. 4x squared minus 3x plus 1. Well, the degree of the term is the power or value of the power or exponent. If the term is a variable term. So actually this is not so difficult, and you're probably, I can imagine some of you at home just writing down everything furiously. Just kind of chill for just a bit and let me get through this, and then we're going to look at a table and fill in that table. And when I fill in that table, I think it'll become really clear. So in this case, let's look at our variable terms. So the degree of the 4x squared term has degree 2, because that is the value of the exponent. Here's our next variable term, minus 3x, and I wrote the 1 there just to remind you that it has indeed an exponent, so that's degree 1. And what about the constant term? Constant terms have degree 0 as long as the constant term is not itself 0, in which case we just say its degree is undefined. When it's 0, we don't even write it, so we don't care about it. So let's look at a few other examples. For t to the 5th minus 1/2 t cubed plus t squared over 100 minus t plus 20. This is a polynomial in the variable t. So let's go through and let's actually identify. This is a constant term, variable term, variable term, variable term, variable term. Now let's think about the coefficients. The coefficients on this term is 4. The coefficients on the minus 1/2 t cubed is minus 1/2. The coefficient of the t squared term is 1 divided by 100, because t squared divided by 100 is the same as 1 divided by 100 times t squared. The coefficient to the minus t term is minus 1, and this is a constant term. It's its own coefficient. Now let's look at the degree. The degree on the t to the 5th term is 5. The degree on the t to the cubed term is 3. The degree on t squared term is 2. The degree on the minus t term is 1. And the degree on the constant term is 0. So that takes care of the case when our polynomial is in a single variable. So for completeness, and there may be one question on your homework or two that requires this, I won't put any on the exam. If you actually are on course to take Calc 3, and some of you might be, I'm trying to think if any of you are, then this will be important. So let's look at a polynomial in the variable x, y, and z. So 4x squared y plus 5z. Right there, I already have a polynomial in the variables x, y, and z because there's an x and a y and a z that appears. Plus 7x cubed yz plus 3z to the 4th minus 1. So this is a polynomial in the variables x, y, and z. Again, just by manner of illustration. This is the constant term. This is a variable term, variable term, variable term, variable term. So let's do the coefficients. So the coefficient of this term is 4. The coefficient of the 5z term is 5. The coefficient of the x cubed yz term is 7. The coefficient of the z to the 4th term is 3. And this is the constant term. If you want to say the constant term is its own coefficient, that's fine. Now what about the degree? So here is the answer. The degree of a term with more than one variable is the sum of the degree or power or exponent of each single variable. Probably could have said that a little bit better, but you'll see you don't have to, number one, worry too much about this. So let's go up here and let's find the degree of let's find the degree. So by what I said, the degree of this term is, well, it's a multivariable term, right? So I take the exponent values on each of the variables and I add them. So the degree of this term is 2 plus 1, which is equal to 3. So the degree of the first term is 3. Here it's just a term in a single variable, so this is a degree 1 term. Here I add up all of the exponents on each of the variables, so the degree here is 3 plus 1 plus 1, so the degree of that term is 5. And the degree of the 3z to the fourth term is 4, and the degree of the constant term is 0. So now we're getting to the most important concept of all of this business, and it's called the degree, not of a term, but of a polynomial. Is the largest degree of any of its terms. So let's go back. So the degree of this term is 3. So this is a polynomial in the variables x, y, and z. And the degree of the first term is 3. The second term 1. The third term 5. The fourth term 4. And the last term 0. The constant term 0. So the degree of this polynomial is the largest of those numbers. So this is a degree 5 polynomial. Up here I have a polynomial in the single variable t, and here are its degrees of each term, 5, 3, 2, 1, and 0. So the degree of this polynomial is the largest of these numbers. So that's a degree 5 term. So let's go up to our first exercise. So here is a polynomial, 4x squared minus 3x plus 1. It's a polynomial in the single variable x. Can you tell me its degree? Well, let's look. The degree of the first term is 2. The degree of the second term minus 3x is 1. And the degree of the constant term is 0. So of those numbers, 2, 1, and 0, 2 is the largest. So this is a degree 2 polynomial in the variable x. When many times we omit the phrase in the variable or variables, but it is more common later on in math, not what you're going to get though. So let's look at exercise 1. So I actually have it here because I want to write on this. So here we have a polynomial and the single variable x. Minus 3x to the fourth plus 7x cubed plus 2x minus 5. So we're asked to list all of the terms. So right here, minus, I think I can write on this. I've been able to write on it in the past. Minus 3x to the fourth is one term. 7x cubed is another term. 2x is another term. And minus 5 is the last term. The coefficient, well, the coefficient of the minus 3x to the fourth term is minus 3. The coefficient of the 7x cubed term is 7. The coefficient of the 2x term is 2. And we just call the coefficient of the constant term itself. So the degree of the minus 3x to the fourth term is 4. The degree of the 7x cubed term is 3. The degree of the 2x term, remember that has a power 1, is 1. And the constant term always is defined to have degree 0 as long as the constant itself is not 0. And we don't have to worry about that because we don't write it when the constant is 0. So now we can literally ask the following question, and you should be able to answer it. Whoops, but not with that color. Color wheel. That should do it. What is the degree of minus 3x to the fourth plus 7x cubed plus 2x minus 5. So this is a polynomial. What is its degree? Well, again, its degree is the largest degree of all of its terms. So this has degree 4. So, not so bad. Let's look at some other things we're asked to do. Okay, it won't be so hard at all. I've already got you more than ready for, not. I guess I could have just gone to the right or the left instead of all the way to the bottom. So let's look at each one of these. So this is 2a. And we're given x squared plus x minus 6. So what is the degree of this polynomial? Well, this is a polynomial in the single variable x. The degree of this term is 2. The degree of the x term is 1. And the degree of the constant term is 0. So this has degree 2. Now let's look at b. 3x plus 10, again a polynomial. So the first 3x term has degree 1, that's a variable term, and the constant term has degree 0. So this is a degree 1 polynomial. And these two right here are going to play very important roles in the remainder of this course. Degree 1 and degree 2 polynomials. Number C, 10x cubed y squared and z. So this is a polynomial in the variables x, y, and z. and its degree is 3 plus 2. Remember, z is raised to the first power, plus 1. So this has degree 6. And then finally, my last one, d. It's the polynomial and the variable z. 8z to the 5th plus 9. So this variable term has degree 5, and the constant term has degree 0. So this polynomial is a degree 5 polynomial. So polynomials in variables are going to be things that we will want to evaluate at the value of that variable. And that's exactly what we're going to do next. So here we have 4 polynomials, and we want to evaluate them for 2 different values of the variables. So our task is we want to let y equals 0, and then over here, about halfway in, we're going to let y equal minus 2. And what we're going to do is we're going to evaluate polynomials. So this is just going to be number 3. We're going to evaluate polynomials with the value y equals 0 and y is equal to minus 2. So let's start with A. I'm given 4y minus 7. So when you say let y equal 0, then I literally replace y with the value of 0 and perform the indicated operation. So 4 times 0 is 0, and 0 minus 7 is minus 7. So the end result is minus 7. So let's do the same polynomial. 4y is equal to minus 2. So again, I have 4y minus 7. So here I literally, the next step is I literally replace the symbol y with its value. It brings its minus along with it. And then I perform the indicated operation. 4 times minus 2 is minus 8. And then I'm subtracting 7 from that. So the answer is minus 15. So let's do B. Y cubed minus 4. Well, let's evaluate it when y is equal to 0. So 0 cubed minus 4 is simply just 0 minus 4, which gives me the final value of minus 4. Over here, y cubed minus 4. Now here again, we replace y with minus 2. And in this term right here, the y cubed term, y is the base, and 3 is the exponent. So the base is minus 2 cubed minus 4. But minus 2 cubed is minus 2 times minus 2, which is 4, times minus 2, which is minus 8. And then I'm subtracting 4 from that, and the end result is minus 12. Now let's do C. I have 3y squared plus 8y minus 9. When y is equal to 0, it's really easy, right? Because that's 3 times 0 squared plus 8 times 0 minus 9. Well, that's just equal to 3 times 0 squared is 3 times 0 plus 8 times 0, so that's 0 plus 0 minus 9. So that just gives me minus 9. What happens, we actually say, when the variable, if it's a polynomial and a single variable, when that variable is equal to 0, we say the variable terms vanish. So if you look over here, 4y minus 7, if the 4y term just vanishes, then my answer is minus 7. Y cubed minus 4, if the variable terms vanish, then my answer is minus 4. 3y squared plus 8y minus 9, if the variable terms vanish, meaning the 3y squared and the 8y, my answer is equal to minus 9. That only happens when we set the variable equal to 0. When the variable is set equal to 0, all variable terms vanish. The only thing left behind is the constant terms. And if there were no constant term, which we will see in the case D, no, it does have a constant term, then the answer would just be 0. So over here, let's do 3. What is it? Yeah, y squared. And again, we're replacing y with minus 2. So I'm literally taking y, which is the base of its power, and I'm replacing it with minus 2, and that's the base. Plus 8 times minus 2 minus 9. Well, this is equal to 3 times minus 2 squared is 3 times minus 2 times minus 2 is 4. Plus 8 times minus 2 is minus 16. So that's a minus right there. And then I'm subtracting minus 9. So 3 times 4 is 12, minus 16, minus 9. That's equal to, well, 12 minus 16 is minus 4, and minus 4 minus 9 is minus 13. And finally, our last one, D. We want to do minus 13 minus 4y minus y squared. Well, again, if I replace 0 for the y terms, all of those y terms are going to vanish, and the only thing remaining is going to be the constant term. Over here, let's do minus 13y minus 4y minus y squared when y is equal to minus 2. So that gives us, there's not a 13y, there's no y here. So that's minus 13 minus 4 times minus 2 minus, remember, the y value brings in its own negative. It brings it with it, squared. So this is minus 13. Minus 4 times minus 2 is plus 8. And minus 2 squared is minus 2 times minus 2, which is 4. So minus 13 plus 8 is minus 5 minus 4, which gives me minus 9. Okay. So let's talk about, before we can do this next exercise, I have to define a new term for you. It's called like terms. There it is. So like terms. That's the definition I'm getting ready to give you. Two or more terms are like if both of the following conditions are true. So what are those two conditions? The first condition, I put these as check boxes. The terms have the same variables. So if this condition isn't satisfied, you're done. They're not like. And if you put a check mark in that first one, then you're still not done. You have to put a check mark in the second box. Each of the variables which are the same are raised to the exact same power. So let's look at some examples here. I'll come over here for my examples. Let's look at x and 5x, 3x squared plus 4x, 7xy and y times x minus 3y squared and 10y. So let's look at our boxes. X and 5x. Do the terms have the same variables? Yes, they do. Are each of the variables, which are the same, raised to the same power? Yeah, each x power is raised to the power 1. So these are like terms. Let's try it again for the next one. 3x squared and 4x. The terms have the same variables. It's their terms, their x, their variables is x, but each of the variables are not raised to the same power. So these are not like. Do it again. 7xy times yx. This is a good example. The terms have the same variables? Yeah, they have xy and yx. They have the same variables. Doesn't say anything about having them in the same order. Just say, do they have the same variables? This is a term in the variables x and y. This is a term in the variables y and x, which is the same as x and y. Are each of the variables raised to the exact same power? Well, the x term is raised to the first power, and the y term is raised to the first power. So those are like terms. In general, what you would do is you would make a decision and you would rewrite y times x as x times y. Why? Because it's multiplication, and the order in multiplication doesn't matter. One last example before we do our minus 3y squared and 10y. Well, they have the same variable because they're terms in the variable y, but they're not raised to the same power, so this is not like. So like, not like, not like. So with that said, let's give you one more concept. 2 combine like terms. So you're talking about terms which are like is to add their coefficients. So the coefficients are, and attach them Let me make that. Of course, I know what I'm writing, but we literally have to deal with students who are not taught how to read in cursive. And it really slows us down. Attach that sum to the variables, like variables. So let's just look at some examples here. I mean, literally just spelling that out makes it more complicated than it really is. So we're going to simplify these expressions by combining like terms. So 3x minus 10x. So this is one term and this is another term. Are they like terms? Yes. So what do? Is I add the coefficients, 3 minus 10, and I attach them to the variable. So 3 minus 10 is minus 7x. And you've been doing this all along. You know already that 3x minus 10x is, well, I have 3 of something, and then I take away 10 of that something, then I'm in the whole 7 of that something. Let's do B. So we have 3y cubed minus 6x squared plus 2x squared minus 5y cubed. So I'm going to start the simplification process by just looking at my first term, which is my 3y cubed term. So I'm looking, are there any other like terms? Yeah, right here is a minus 5y cubed is a like term. So I'm going to put those side by side. And when I do that, I usually just kind of mark through them, because when I'm transferring them down, I may forget a term. And then I just start with my next one, which is minus 6x squared. And is there any other like term? Yeah. It turns out that 2x squared is a like term. So now all we do is we add their coefficients. 3 minus 5 is minus 2. And I attach the variable. Minus 6. So again, these are like and these are like. So minus 6 plus 2 is minus 4. And then I attach the variable along with its power. So let's do number C. Oh, are you kidding me? Let's just do number C. I'm going to change number C's different. I don't see any reason why they're suddenly making you add and subtract variable. It's not that hard, but you know, if you're learning something like combining like terms, let's just concentrate on doing that instead of throwing decimal addition at you or subtraction at you. But we're going to go ahead and do it. So again, let's start down here with the combining process. I'm going to start with my first term, which is 3.7x cubed. So 3.7 is my coefficient. Now I've copied it down there. Is there any other x cubed terms? Yeah. There's a minus x cubed. And that's it. So these are like terms. You don't have to put the underline there. I'm just doing it right now to help. Now I start with my next. Minus 6.3x. So I've written it down there. Is there any other x terms up there? Yeah. Plus 11.6x. So those are like terms. And then I have my constant term, 8.2. So here what we do is notice that the coefficient of minus x cubed is minus 1. So this is 3.7 minus 1 x cubed. Over here, I add the coefficients, which is 11.6 minus 6.3 x. Then I subtract 8.2. So 3.7 minus 1 is 2.7 x cubed. 11.6 minus 6.3 is plus 5.3 x. That's the only reason I decided to do this, is because these are pretty easy decimal additions and or subtractions. So let's do something that I bet you can do really well. Let's identify the degree of each polynomial. So 5a, because we've done that. So remember, the degree of a polynomial is the largest degree of any of its terms. And it's really only difficult if the polynomial is in more than one variable, and literally everything they give you is a polynomial in more than one variable, other than the first one. Other than, sorry, the second one, b. So 5a, we have 2xy minus 5x plus 6xy. So the degree of this term is 2, because I just add the exponents. That's 1 plus 1. The degree of this term is just the power of the exponent, which is 1. And the degree of this term, I add the exponents, and this is 2. So this is a degree 2 polynomial. I'm just going to write poly in the variables. X and y. So we will do 5b. 4a cubed minus 3a plus 6. Well, the degree of the first term is 3, the second term is 1, and the constant term is 0. So this is a degree 3 polynomial in the variable a. Let's do 5c. It's x cubed y minus x squared y squared plus x y cubed. So the degree of the first term, I add up the exponents, so that's a degree 4 term. Add up the exponents, that's a degree 4 term. Add up the exponents, that's a degree 4 term. So this is a degree 4 polynomial in the variables x and y. And then the last one, let me get some more room up here. I'll just bring it over here and do 5d. And we have s to the 5th t squared minus 3s to the 4th t plus 5st. So this is a polynomial in the variables s and t. The degree of the first term is 5 plus 7, well, it's 5 plus 2, which is 7. The degree of the second term is 4 plus 1, which is 5. And the degree of the last term is 1 plus 1, which is 2. So this is a degree 7 polynomial in the variables s and t. So there is, especially for computer algebra systems, it helps if we write polynomials, because if you have a whole bunch of sums, the commutative property of addition says you can arrange those sums in any way you want. But what we want to do is we want to arrange them in descending powers. So let's look at the first one. And we don't want to have any missing powers. So let's look at 6a. 6a is 3 plus 5x cubed. This is a degree 3 polynomial. So we want the degree 3 term first, degree 2 term after that, degree 1 term, and the degree 0 term, which is the constant term. So the degree 3 term is 5x cubed. And the constant term is 3, and that's a plus 3. So what happens? There is no degree 2 term, and there is no degree 1 term. But I can add them in there by writing 0x squared plus 0x. So that's literally what you want. I really don't understand why they want you to put with no missing powers, because really what we would want to see is just 5x cubed plus 3. That would be sufficient. But that's what they're asking us to do, so that's what we will do. So this is 6b. So again, I have minus 8 minus x squared plus 2x cubed. So this is a degree 3 polynomial. And whenever you're asked to do this, all they do is polynomials in a single variable, because the arrangement in descending powers takes on different forms. And that's something I actually just learned in my last graduate class, the very last one I took. So this is degree 3. So I'm going to want my degree 3 term, a degree 2 term, a degree 1 term, and a degree 0 term. So the degree 0 term is minus 8. This is the degree 2 term. And this is the degree 3 term. The degree 1 term is missing, so I put plus 0 times x, and it's x raised to the first power. So let's do 6c. It's a polynomial of the variable m. 3m cubed minus 5 minus m. This is also a degree 3 polynomial. So again, we'll have 3, 2, 1, 0. The degree 3 term I write first. The degree 2 term is missing, so I just put minus 0x squared. The degree 1 term is minus m, and the constant term is minus 5. And 6d, I have 3r minus 4r to the 5th. So this is a degree 5 polynomial in the variable r. So I have to have a 5, 4, 3, 2, 1, 0. So the highest degree, always notice, the highest degree always has to have something underneath of it. So that's minus 4r to the fifth. There is no degree 4 term, so that's plus 0r to the fourth. There is no degree 3 term, so that's 0r cubed. There is no degree 2 term, so that's plus 0r squared. The 3r is a degree 1 term, plus 3r, and there is no degree constant term, but as I said earlier, we don't ever write plus 0. We just leave it out. Why is this not erasing? Oh, because I'm hitting the wrong button. Well, just try it again. We don't want the 0 there. So if there's a missing constant term, you don't bother to write in 0. Okay. So I have one other thing I want to talk about. So we've classified polynomials by their variables and their degrees. But there's one other really common classification, and this is a classification not by degree, so the degree is irrelevant, but by the number of terms. So, number of terms. I actually find this the least helpful of all classifications. For some reason, books like it. So number of terms and classification. That's the reason I saved it to the last. So many ways to classify. I think really the degree is the most important classification you can get. So the number of terms, you have to have at least one term to have a polynomial, and that's called a monomial. So for monos meaning one, and I took classical Greek, and I'm not for sure about that road. It could be a mixture of Greek and Latin. It could be all Latin. If you have 2 terms, then it's a binomial. If you have 3 terms, it's a trinomial. And over 3, no special name. The thing I want you to remember is all of these are polynomials. So a monomial, an example of each. Let's do an example of each. 3x, that's a monomial. X squared minus 4, that's a binomial. 3x squared plus 2x minus 1, that's a trinomial. Over 3, 3x to the 6 minus 4x plus 5x squared minus 2x to the 5th plus 1. So the only thing that you can say about the degrees is really nothing. Really nothing at all. So this is purely a classification by the number of terms. If I want to talk about the degree, I can say a degree 6 monomial. So this is a degree 1 monomial. This is a degree 2 binomial. This is a degree 2 trinomial. And this is a degree 6 polynomial. But the important thing to remember, all of these are polynomials. These are just classifications of special types of polynomials. Like a cow, a horse, and a dog are special types of mammals. And that's it for lecture 12.3.